Welcome, everybody, to today's Transfer Lab seminar. The Transfer Lab seminar is part of the Applied AI Institute for Europe. And our seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning. And today we have a talk by Christian Geishauser, who will talk about his PhD topic, which is dense rewards and continual RL for task-oriented dialogue policies. Christian is a generative AI engineer at the Innovation Lab at the Applied AI Initiative, and he joined in May 2024. And prior to that, he finished his PhD at the Heinrich Heine University in Düsseldorf. He has also a bachelor and master's degree in mathematics from the LMU Munich. And we are looking forward to your talk today to learn more about your background and what you did during your PhD. And with this, let's welcome Christian, and we're looking forward to your presentation. Thanks for coming today.
Yeah, thanks a lot for the introduction, Samuel, and thanks a lot to Miguel and Samuel for giving me the opportunity to present my work here. So this is based on the PhD defense presentation that I was holding in late April. So this was 30 minutes long. So I tried to extend parts that might be interesting to you in general and provide a bit more details. So just for you to know, I don't have a second screen right now, so I can't see you. So if you want to interrupt me, just let me know, please. All right, but I think someone said everything at the beginning, so I can just start here. So for the outline, at the beginning, I will give a brief introduction to task-oriented dialogue and dialogue policies, because that is the topic that we will center around today. During the talk, we will look at different challenges in reinforcement learning for dialogue policies. In particular, there are three we will have a look at. The first is sparse reward problem. The second one is the absence of continual learning dialogue policies. And the last one is the absence of realistic continual learning environments. And afterwards, we will just wrap up with a brief conclusion. All right, so just to get started, let's say that dialogue is the fundamental way of communication between humans, and there are infinitely many dialogue topics you can talk about, basically just limited by your imagination. In the talk today, we will focus on a dialogue between a user and a dialogue system. And moreover, we will center around so-called task-oriented dialogue. So what is task-oriented dialogue? In task-oriented dialogue systems, they help users to achieve a specific task or goal during interaction. So this could be making a hairdresser appointment, finding attractions or activities for a trip, finding restaurants or hotels to book in town, and many more. So regardless of the specific task, the main objective of the dialogue system is to fulfill the user goal. And these task-oriented dialogue systems, they always operate within certain boundaries that are defined by a so-called ontology. The ontology is typically comprised of domains, which could be restaurants, hotel, trains, for instance. There are slots within a domain. So for instance, the hotel price, the area, the day you want to make a booking, and the number of people. And there are values for every domain slot pair. So for the domain slot pair hotel area, maybe you can specify the value being north, east, west, or center. And for the price, it could be cheap, moderate, or expensive. So this is usually constraints that the user can set for the goal he or she has in mind. Moreover, we have semantic actions, and these are defined through domain intent slot triplets. For instance, this could be hotel inform address. So the system wants to give the address to the user where the hotel is located, or hotel request price. So you want to request the price range the user is interested in. We can say that the ontology defines what the system can understand through these domain slot value triplets, and the ontology defines what the system can say through these semantic actions. Typically, in the scenario we will see today, we will focus more on this semantic space and not the language space. These task-oriented dialogue systems, they require at least two abilities. The first ability is to maintain the current state of the dialogue, which is referred to as tracking. So this is typically done through a belief tracker. And this belief tracker tries to maintain a probability distribution over values for every domain slot pair. We will see later an example how this looks like. And the second ability is acting. So we want to take actions that lead to user goal success. And that is the responsibility of the dialogue policy, where we will focus on in today's talk. To make everything a bit more tangible, let's just have a look at one example. So you have a user, and we assume this user has some goal in mind, and the user starts a conversation by saying, I need an affordable restaurant in the north. So this textual representation will then become input to this belief tracker, and the belief tracker tries to extract semantic information from the text. So it's very common that we try to extract the user act. So here the user act is that the user informs that the restaurant price should be probably cheap, and also informs that the area should be north. Moreover, it extracts these user goal belief state distribution. So here, for instance, for the domain restaurant and for the hotel price, you have this distribution over the possible values that are defined through the ontology. And you can see that the belief tracker is not quite certain whether it should be cheap or moderate price range, because affordable could be kind of both. It's not really clear at this point. But you can also see that belief tracker is quite sure that the area should be north. So this semantic representation will become input to the dialogue policy then, which decides on an action to take. In this case, it could be restaurant select price, because we want to resolve this uncertainty in the price range. And typically this semantic action will then go into a natural language generation component that produces some textual output in the end. So this could be then, should it be cheap or moderate? And then user obtains this text, answers by saying a cheap one, please. And then this dialogue continues until it's finished at some point in time. Once it's done, you can take the whole dialogue and you can take the user goal and try to assess whether this dialogue was a success or a failure, basically, which is like the most important thing for us in task-oriented dialogue. So with this example, you can see that dialogue policy has to solve a sequential decision-making problem, which is finding actions that lead to fulfillment of the user goal. And we can try to optimize dialogue policy using reinforcement learning. So in reinforcement learning, you have an environment which is given by the user in our case, and you have a RL agent, which is given by the dialogue policy pi for us. Now, on every turn of the conversation, user sends reward RT and observations to the dialogue policy pi. The policy in turn sends action back to the user. And the goal of the dialogue policy is to maximize the episodic return in expectation. So here episodic return is this sum of the rewards RT weighted by this discount factor gamma that favors rewards more close to the point in time over future rewards. And considering the definition of reward, it's common that we give a high positive or negative reward at the end for dialogue success or failure, and a small negative reward, for instance, -1 in every turn for making the dialogue more efficient. And so this is what also differentiates it from chatbot, because their user engagement is usually one of the objectives. So you want to engage in a dialogue as long as possible, whereas here we want to make it as efficient as possible. So this reward definition brings us to the first problem, which is that the informative reward is only received at the end of the conversation. So we can say that this reward is sparse. So here you can see that in every turn, the reward is -1, so there's no information in it, basically. And at the end, it's typically 80 or -40, so for success or failure. And so this leads to requiring many interactions to find an optimal solution, and a low sample efficiency due to the correct assignment problem, because it's not so easy to really find the actions that really contributed to success or failure. So yeah, as another example, it's a bit like you play chess and then in the end you win or lose, and then you need to find the moves that actually contributed to your win or you lose. So here we asked ourselves, how can we obtain dense rewards for more sample efficient learning? And the observation we had was that dialogue policy needs to know two things. The first is, what is the user goal? So this could be that the user needs a cheap Italian restaurant and a reservation for Saturday 6 p.m. and user requires a phone number and the address. And once we know the user goal, we need to know how to solve the task or goal actually then. So we need to book the restaurant table maybe, and inform the phone number and the address. So here it's important to say that the task can be only solved once user goal is known. So can we somehow encourage that behavior that gathers information about the user goal? To this end, we proposed in this work information gain as a reward for solving the sparse reward problem for dialogue. And so this information gain encourages actions that lead to information gathering about user goal, and it can be calculated in every turn of the conversation, making it a more dense signal. To see how this is calculated, it's very easy actually. So we use the example we just saw, where the user said, I need an affordable restaurant in the north. System says, should it be cheap or moderate to resolve the uncertainty? User answers with a cheap one, please. And after that, you can see that now we are much more certain that the price should be actually cheap now. You have a change in distribution now, and we interpret that change in distribution here as a gain in information. And then in order to calculate this information gain reward, we kind of calculate the similarity between the two distributions here. In the experiments, we used the Jensen-Shannon divergence because this gave us a bounded reward that was a bit easier to handle compared to KL divergence, for instance. All right, then just for experiments, here we leveraged an architecture which is called feudal dialogue management, abbreviated with FuelRL. And this is a hierarchical architecture where you not only have one policy, but actually you have two policies. And these policies operate on dedicated action spaces, basically, that you predefine beforehand. So we have one policy, PyInfo, which is responsible for gathering information about user goal, for instance, by confirming, requesting, or selecting information. And we have another policy called PyGeneral, which is responsible for actually solving the task. So informing the user about the address or the phone number, booking hotels or trains, or recommending information. And in FuelRL, both of these policies are optimized by maximizing this sparse success reward. We propose that for this PyInfo policy that is responsible for gathering information, we optimize it for maximizing information gain, actually, because we thought that's a more appropriate reward signal. And moreover, in experiments, we also compared to the previous state of the art back in time in 2018-19. So when you run these experiments or these trainings, you typically have different domains you evaluate it on. So here we had Cambridge restaurant domain, San Francisco restaurant domain. So it's both about restaurant, but they distinguish in the number of slots and values they have. Then we have the laptops domain. So these were the three domains that were accessible for the framework we had back then. And we also use different user simulators. So at this point, it's good to say that I told you that the environment is the user, but interacting with real users would be too costly for training and also too unstable. So usually we always refer to user simulators. And in the group I was working on, and there was one PhD student who was only working on these simulators, actually. All right, then just having a brief look at the results here. You see the number of training dialogues at the x-axis, which is 4,000 in total. And you see the sum of rewards per episode. So we evaluate these policies at some certain points in time. And you can see that if we use information gain for optimizing this information seeking policy, we get much higher starting performance. So this means more sample efficiency and also higher end performance. And yeah, you can also see that there's a lot of variation in the baseline. And so this is because oftentimes when the algorithm is not so strong, you tend to fall into a local minima where the policy tries to end the dialogue as quickly as possible because you have this term penalty in every time step. And if you can't find successful dialogues, you just try to end it. And this leads to these huge variations that you see here. And then we also compared to Strack just here after 400 training dialogues, where we achieved high success rates. So also confirming this better sample efficiency because we have a more dense reward and more or less same success rate in the end. And then one thing we always need to do, or I always had to do when I publish a paper, I need to let these systems interact with real users because I need to show that the results not only hold in simulation, but also like in the real world. in exclamation marks maybe. So here we use Amazon Mechanical Turk always, where these Turkers could interact with one of the two systems. So they have a user goal at the beginning, and then they need to conduct a conversation. And afterwards, it's just a small survey where we ask them whether the dialogue was successful, how was the overall performance. And in this specific case, we also asked whether the systems ask for information if necessary, because we wanted to show whether this information gain changed the behavior a bit. So to really encourage this information seeking style. And you can see that this actually is done here. And I was happy about that, because when you train these dialogue policies from scratch, then oftentimes they really want to give you information from the beginning onwards, because that's usually required in order to be successful. And I think that when you have a natural conversation with a human, then it's more natural that you first ask, like, what do you actually want? What's your price that you're interested in? And so show some interest. This could be achieved through this reward here. And so here I just showed you this information gain as a dense reward for increased sample efficiency. So that was the first work I did back then. And there's a but to it. And this is that, as is commonly done, I tested the model on a fixed environment. So with a fixed ontology and with a fixed amount of domains. So I defined the ontology beforehand, and I said, maybe you can talk about hotels, about restaurants, and about taxis, but that's it. And we fixed it. But then what happens if you want to add new domains to that ontology? Maybe at some point you want to say this dialogue system should be capable of talking about trains, you want to make train bookings, or you want to help users find attractions somehow. And then you can ask yourself, can a system still interact successfully? Can a system continue learning more like humans actually? And this brings me to the topic of continual learning here. And this is to say that the world is ever changing, and there's a vast amount of tasks a dialogue system can assist with, and more are upcoming in future. So just imagine for the pandemic, there could be a dialogue system that helps you make COVID vaccination appointments, for instance. A dialogue system needs to continue learning to assist with more tasks over time. Being a bit more precisely about continual learning, this usually focuses on non-stationary or changing environments. And it's very common that this continual learning setup is divided into a set of tasks that need to be completed sequentially. So you learn on some task 1, then you switch to task 2, and then to task 3, and so on. So when you think about continual reinforcement learning, these different tasks are usually defined through different Markov decision processes. An alternative way is also to say that now you have a Markov decision process, CRL, where state space, action space, reward function, and transition probability can depend on time. This has been done in this Continual RL survey by Ketapal et al. But oftentimes you see this definition where they just say it's a sequence of tasks. And so compared to multitask learning, we do not see all the tasks at once, but only sequentially. Compared to transfer learning, we still care about previously observed tasks. And lastly, compared to curriculum learning, we have no influence on the task order. There are a couple of continual learning challenges. So imagine you have a learner and this learner learns on task 2 at the moment. Then the first challenge is forgetting or catastrophic forgetting. So the performance on all tasks should not decrease when learning on a new task. You don't want to forget how to solve task 1. The second one is forward transfer. So you want to leverage the past knowledge in order to improve performance on future tasks. And usually you assume that you only have limited resources. So limited resources in terms of model capacity and memory. And these different desiderata points, they are competing with each other. So in human brain, this is referred to as stability plasticity dilemma, because if you want to prevent forgetting, you want to be very stable. But if you want to adapt quickly to new circumstances and have this forward transfer, you want to have plasticity, and our brain solves that dilemma somehow very nicely. And also you can say that if I want to prevent catastrophic forgetting, okay, I just keep all the training data I've ever trained on. I just keep that into memory and keep training on it. But this is then in conflict with this limited resources. So there's a bit of a balance you might need to do. So here just a note on catastrophic forgetting to visualize it briefly, because catastrophic forgetting is something that most people in continual learning were focusing on. So let's imagine you train on task 1. You find a nice solution here in this 2-dimensional weight space. Afterwards, you just continue learning on task 2 and you don't have any kind of regularization. Then what could happen is that you move away from the solution you found towards a solution that works for task 2. And in contrast, when you have multitask learning, for instance, or you learn on both tasks at the same time, you have this kind of tug of war dynamics where each task pulls from different sides, and you maybe find a solution that works for both tasks. But what can also happen is that tasks interfere with each other, and it's actually not possible to find a solution that works best for everything. And here just some examples from real life or machine learning. So in real life, when you're a little baby, you first learn to crawl, then you use the motor skills to learn how to walk, then to jump, then to run. Maybe you learn different programming language one after the other. And once you learn Java, you don't forget how to program in Python. You learn different sports. In machine learning, you might want to classify new image categories over time. In RL, you might want to learn different Atari games one after the other. And also in autonomous driving, when you have changing tire frictions over time, also changes the MDP slightly. Also, when you have the different LLM training stages, usually you have pre-training on large corpus first, and then you move on to instruction fine-tuning, and then you move on to reinforcement learning from human feedback, where you try to maximize this learned reward function. Usually you have this regularization term, which can be interpreted, I think, as a kind of prevention of forgetting. You don't want to overfit to the reward function and forget how to actually follow these instructions and talk nicely. But let's come back to the actual topic, which is continual learning for task-oriented dialogue here. In our case, tasks are usually defined through different domains. So first you talk about attractions, then at some point you talk about trains, and then hotels and so on. This is the step that has been typically done. And here recall that the ontology defines what the system can understand and what actions it can take. And now there is some information that we need to comprehend. So the hotel price, for instance, this is not set. Usually we have none value for that then. Hotel area is north, and maybe the user wants to request the address. So there's some information we have to comprehend. And we have some possible actions we can take. We can request a price, we can offer to book a hotel, we can inform something. And when we want to use neural networks, we somehow need to find vector representations for these things. Commonly, it was the case that you just use binary representation. So whenever there's an information present, you give it a 1, and otherwise you give it a 0. For the actions, you can actually choose multiple of these actions at the same time, because maybe you want to inform on the address and you want to inform on the phone number. So these are different atomic actions, and actually you can combine them. So here you just, for every action you have, you can say whether you want to use it or not. Now, when the ontology grows as more domains are seen, because you introduce a strain, the information you need to comprehend becomes larger, and also the possible actions you can take becomes larger. So you get a larger state and action space now. So the apparent disadvantage of these binary representations is that this vector gets larger and larger the more domains you introduce. And also there is no semantic meaning about what this information actually contains here. And then researchers moved towards learning embeddings for these different information in order to have some semantic meaning, or learning some semantic meaning. And then because this, again, list of vectors can become very large, they use some averaging over this information in order to keep it bounded. So this averaging then can lead to information loss if this becomes very long. And if you learn these representations, you don't have any zero-shot capabilities at the beginning. For these dialogue policy challenges in continual learning, we ask ourselves 3 questions here. The first is, how can we incorporate new information and actions into a model most efficiently? So how can we tell the model what a train destination is, or what does it mean to book a train? Secondly, how can we deal with the ever-growing number of information as domains are added? So imagine there are hundreds of domains we can possibly talk about. How can we keep this information bounded? And lastly, how can we talk about new domains in a zero-shot fashion? So the user comes and says, I need a train on Sunday, but you have a system that only learned to talk about hotels. Very likely that it will respond with something about hotels again. So in summary, we asked here, how can we enable continual learning for dialogue policies? The first observation we had here is that every information and action is describable in natural language. So you can describe what the hotel price is, what the area is. So nowadays, it would be common to put that into the prompt of an LLM and just explain it there. Back then, we didn't have that, so we used a Roberta language model. We put in this natural language description and obtained different embeddings for that. And these embeddings for every information becomes then the input to a transformer encoder that we will train from scratch here. By using these language models, which have some pre-trained knowledge about what this information contains, we hopefully have some zero-shot understanding of new information that once you introduce trains, maybe it already knows what a train is and so on. So we get this list of vectors then. Secondly, we want to bound the information to process because maybe this information list is just too long. And here what we do is a very simple approach. We just say that in a specific dialogue, there's some domains that are mentioned. So maybe the hotel is mentioned. The other things are not mentioned yet. So we just use a hard attention mask in order to bound this information and really just focus on the information that is necessary in some point in time. I think nowadays, maybe in RAG, you have this metadata filtering. So maybe you can say, I filter based on the domain I'm interested in. Something like that is maybe a comparison here. All right. And then lastly, we had this question about how to talk about new domains in a zero-shot fashion. My idea here was that I want to abstract the question about the domain to choose first. So in order to directly say what is the domain I want to talk about, I did the following. So when the user says, I need a train on Sunday, I first ask myself, do I want to talk about the same domain as the user? Or do I want to talk about something else? It's a bit more general then. And the architecture that I developed here, which is called DDPT, which stands for Dynamic Dialog Policy Transformer, I introduced a domain gate that produces a probability P of talking about the same domain as user or about something else. So that is something, some small neural network that will be learned in the process. When it actually comes to how to produce actions, it's not like that for every atomic action, we make this binary decision here, but we auto-regressively produce triplets of domain and then slot. So for instance, hotel, then request, then area, and so on. So this is basically like predicting one token after the other, but in a constrained token space that is defined by this ontology that tells us the things we can talk about. So just briefly how this is done, we have this transformer encoder that tries to extract some good representation from the input information. And then we have the transformer decoder that's just prompted with this start token that now decoding starts, and a domain token that says that now we want to start producing a domain. And then we have some possible domains we can choose from. And we use this language model again to produce embeddings for each of these domains. And then we can calculate similarity based on dot product, for instance, with the transformer decoder output and these domain embeddings. But this alone will not lead to talking about new domains in a zero-shot fashion. So we have this additional domain gate that will reweight the probabilities based on whether we want to talk about the user domain or not. And somehow together with that, we get this domain distribution. We sample from it, we get hotel, for instance. The next step, we then want to predict an intent. We tell the transformer that we just sampled the hotel domain, and then we just do the same process as before, but this time we have possible intents that we embed through the language model. And here we just take similarity, but do not use the domain gate because that's just for domains. And we sample intent, for instance, request. And then we do the very same thing with the slot here, where we say we just took the request. And afterwards, you can finish the process or you can continue producing more of these action triplets. For the experiments, we tested that on different task sequences. There's not one task sequence that should be preferred over another one. But for instance, one sequence we chose is we talk about attractions first, then taxi, then train, then restaurant, and then hotels. And once we are done with that, we repeat that cycle one more time. There was really common in the literature there. We use 5 domains from MultiVoice 2.0. So this is a data set for task-oriented dialogue systems where you have multi-domain dialogues. So within one dialogue, you can potentially talk about multiple domains. So for instance, you want to find a restaurant and then book a taxi that brings you there. So that was the most common data set we had back then. And based on that, an RL framework with user simulators was built. And all of these models are optimized using CLIA. And just for the RL enthusiast, just one slide about how this CLIA algorithm works briefly. So remember that in continual learning, we want to prevent catastrophic forgetting and we want to improve fast adaptation. So for the fast adaptation, the authors from DeepMind, they said that, we just do something that's very simple. We want to utilize online samples for the updates in addition to the replay buffer experience. So we gather a new experience and we take that immediately as a way for fast adaptation in addition to sampling from the buffer. And for preventing forgetting, they sample experience from the replay buffer and then they use a KL divergence loss for regularizing the actor policy towards the behavior policy that used to generate this experience. And for the critic, they have some mean squared error loss for regularizing the critic towards the old prediction. Just a formula. So you have the behavior policy mu, you have the target policy pi theta that we train. You calculate KL divergence here for this policy cloning or regularization. And then for the critic, you also just have this mean squared error between a current critic prediction and the prediction you used to do back in time. As base algorithm, they use off-policy actor critic algorithm vtrace that I also use. Because this is an architectural proposal, there are some architectural baselines. So first is that we use these binary features that does not encompass any semantic meaning. We have semantic state representation that are learned and then using a simple averaging mechanism that is to be done. And lastly, we have something we call gold, which is a upper bound. And this is obtained through training an expert model on each of the individual domains until convergence. So for the results, here you can see the average performance across domains. You can see that we trained for 16,000 dialogues in total. And after 8,000 dialogues, we repeat this, or the second cycle starts where we just follow this domain sequence again. Here, this green horizontal line is the goal, the upper bound. So at some points in time, we take each of the policy, we evaluate it on each of the 5 domains we have, and then we take the average over the domains to see how well they perform on them together, basically. And you can see that the DDPT model quickly accelerates and is constantly increasing. And this indicates strong forward transfer because at this point in time, DDPT has not seen all of the domains yet, but it still seems to perform good on some already. And you can also see that we achieve upper bound performance here with a fixed size number of parameters. So we don't need any extension of the neural network for that. And you can also see that baseline struggle on the first cycle. And this indicates forgetting and weak forward transfer, as we will see in a second. So it's not like that the models do not learn. They learn indeed, but they forget afterwards. And that's why it looks so horizontal in this first cycle. And you can also see that the second cycle is necessary here. So we also measured forgetting, which is performance decrease on old tasks after training on new tasks. So here, the lower, the better. And you can see that DPT has almost no forgetting. I think this is due to this language model embeddings that are frozen and more robust, and also due to this domain gate that mitigates the problem of choosing the correct domain. Here's just one plot where you can see, again, the training dialogues on the x-axis. You can see the success rate only on the domain attraction. And here you can see that all of the models, so also the baselines, they actually learn on attraction, but afterwards they face this catastrophic forgetting when they start learning on the other domains. And then you can see here, once the second cycle repeats, they start learning attraction again. So here you can really nicely see how this catastrophic forgetting occurs. Then secondly, we measured forward transfer, where the higher is the better. So this is performance on unseen tasks. And again, DDPT performs much better here. So this is mostly due to this domain gate that I was talking about. So I did some ablation here and we said that this gave a big leap in performance, because if you're not talking about the right domain in the first place, it's not easy to fulfill the task at all. Just in summary again, so here in this work, I was proposing this DDPT architecture to enable continual RL for dialog policies. The continual learning setup was that we saw these domains sequentially, and each of the domains was observed for a fixed amount of time. And this is an adequate environment for measuring forward transfer and forgetting, because if you don't see a traction domain ever again in your life, it's very hard to not forget it. So this becomes a really hard problem then. But you can ask yourself how realistic that actually is. So I think it's quite unlikely that a domain will disappear once another domain is introduced. If you think about Apple Siri, if maybe they introduce a new service where you can make hairdresser appointments, but then you can't find restaurants anymore, I think that's not quite likely. Usually it just expands the capabilities. And you can also ask yourself why you actually want to evaluate a system on a domain that you will never see again. Why do you still care about that then? What we can say for sure is that continual learning dialog systems face various circumstances. So usually you have multiple domains that can emerge within a dialog. So as I said, maybe you want to find a restaurant and also book a taxi that brings you there. The system experiences a multitude of user behaviors, and the user demands can also change over time. So for instance, due to seasonal changes, where in vacation season, maybe hotels are more demanded compared to some other domain. Back in time, none of these circumstances were modeled in continual learning dialog policy setups. Moreover, I asked myself here, how should I actually evaluate these continual learning dialog policies? The first question was then, how can I build more realistic environments for continual learning? And then I proposed this more flexible and controllable framework that I call the record. It tries to model all the things that I just mentioned. So as before, you start with one domain, which could be attraction, and then you introduce another domain, which could be train. And now on record, you can still talk about attractions compared to before, and you can also talk about both domains at the same time here, emphasized through this overlap in these circles. And once you introduce yet another domain, of course, the same holds. I also try to model different user demand changes. And moreover, I also modeled these multiple users. So I try to make this setup much more versatile and more realistic here. And this is a strict generalization to the setups before, and it's not something else, but something that is more general. So you can still conduct the old setups here. Secondly, I asked myself, how should I evaluate continual learning dialog policies? Then I thought that these continual learning agents should not be evaluated on how well they perform on tasks or domains that never occur again, because in the end, humans also forget over time if knowledge is not required. Instead, I thought that these agents should be evaluated on how well they perform during their lifetime, and they should try to be as good as possible on circumstances that are actually observed during learning. Because of that, I decided to evaluate the agents on their lifetime performance in this work here. Next, I asked myself, how should I optimize continual learning agents? So because dialog is an episodic task that has some end at capital T, these models are optimized for episodic return, as we've seen in the introduction. So this optimizes for the present. So for the current circumstances, you talk about dialogues, about restaurants, so you optimize for restaurants. But it does not take into account these changing circumstances in the future that can occur in continual learning. So a more long-term view maybe. So because of that, I propose to include lifetime return into the optimization. This is a very simple change here. So instead of going at a capital T, you go into infinity. So you measure the lifetime return and use that for optimization as well. And lastly, these RL algorithms, they often have additional loss terms that affect learning. For instance, in the clear algorithm, you have a entropy loss to maximize entropy, which makes just the behavior a bit more versatile and helps in exploration. And you have this regularization loss where you want to regularize towards past behavior. And this alpha and beta are just hyperparameters that influence how much emphasis you put on these losses. Now, these optimal hyperparameters, they can vary throughout the lifetime of the dialog systems. Maybe when you have new circumstances, you want to have a bit more entropy to explore more. Maybe at some other points in time, it might be beneficial to regularize more towards the past. Because of that, I propose to meta-learn the hyperparameters towards maximization of lifetime performance. So I want to use, for instance, this loss term only to the extent that it helps me in maximizing the future lifetime performance. I just want to briefly say, because I'm not sure everybody is familiar with meta-learning, just one slide on the recap here. So in meta-learning, you have usually two models, which could be potentially the same model actually. You have a base model and you have a meta model. And you also have two phases. You have an inner loop update and you have an outer loop update. And in the inner loop update, you want to optimize a base model parameterized by theta I using the meta model predictions in some way. And you can make capital M, many of these inner loop updates. And once you did that, you perform an outer loop update. So you want to update the meta model eta based on the updated parameters of the base model. So for instance, you have this base model parameters, then you make an update of theta using this meta parameters. So for instance, it could be just the learning rate. And then when you adjust the parameters based on the gradient, these new parameters, they effectively depend on the learning rate, or they will also depend on the hyperparameters that I set for these loss functions on these weights. So that's how I use them. And then you conduct these different inner loop updates. And at the beginning, you get these new parameters that now depend on the meta parameters. And now you make a gradient or an update step by calculating the gradient of this thing with respect to eta. So then you backpropagate all the way here. So for the experiments, this has been tested for different settings. So we had AppP, which was the abbreviation for optimizing for episodic return. And we had live to optimize for lifetime return, AppP plus live that optimized for both at the same time. And lastly, we had AppP plus live plus meta, which optimized for episodic and lifetime return, and additionally had this meta learning of hyperparameters. As in DDPT, we use clear as base algorithm here. And first, we just have a look at the average lifetime return for the whole lifetime for different optimization objectives. Here we can see that using lifetime or combination improves performance, and additionally using meta learning of hyperparameters brings best results. But it's just some overview. So let's have a look at a bit more into the local performance. So here we measure the average success rate within a time window of 500 dialogues. So we have 500 dialogues. We just take the mean of the success and then we move that window over our whole training dialogues here, 24,000 in total. And so on these points in time, we introduce new domains into the system. And here in this last part, we change the user demands every 1,000 dialogues. And you can see that the performance drops when new domain is introduced. So for instance, if you use the traction, you see domain drop, the drop for all systems, but you also see that all models adapt over time after domain introduction. So this just a sanity check that everything works as expected. But you can also see that, the models or the proposed methods here, they perform also better locally. Maybe I just skipped a slide. Of course, you can also have a look at how these loss weights, they decrease over time during meta learning. But let's just come to an end, I think, here. So here in this work, I presented the record framework for realistic environments for continual dialogue policy learning, and also lifetime return optimization and meta learning for enhanced continual learning. And just some future work that I would have found interesting. The first is thinking a bit more about this improved adaptation of continual learning agents, for instance, using other methods like episodic memory or enhanced exploration mechanisms. And in terms of reward learning, it would be nice to learn intrinsic reward functions during the lifetime of the agent that also adapts to the circumstances. And then lastly, of course, large language model integration. So how can we utilize generalization capabilities of these LLMs for fast adaptation, continual learning? And how can we combine task-oriented dialogue system modules with LLMs? All right. Thanks a lot for listening. It was a bit over time, I think, but that's the end of my talk, and I'm looking forward to questions.